Everyone, welcome to this video where we will continue solving problems with the commutators. Here we will solve these two commutators of angular momentum, the commutator between angular momentum and linear momentum, and also this, which is the commutator between different components of angular momentum. We will begin solving the first one, and we have this definition for both. And we go on here. We have commutators of the x component of angular momentum with the x component of the linear momentum, and by definition the x component of angular momentum, we have this expression. Then we will substitute here. We have y pz minus z py px, and we have now this we can take as a sum of two commutators, which is y sorry pz and px minus this minus z py px. And for now we can apply the rules that we have learned in the previous video, or where we was talking about the commutators, the first video where we was talking about commutators, where we have solved a lot of exercises about. And the first exercise was to demonstrate the properties of commutators between commutators, commutators of operators. Okay, and we will apply here. We can see that we can apply we must apply the rule a b c, which is equal to a b c plus a c b. Then we'll apply this rule, and we have now this has equal to y pz pz px plus y px, and here minus z py px minus y, sorry, here it's minus z p y x time p y. Okay, and we can see, for example, that if we have, sorry, I'll put here, and we can see that pz py, when we apply this to a function, we have pz px minus px and pz psi. And we know that the linear momentum is associated with the first derivative. We have, for example, I can write this as h bar square d of z, minus here, because we have minus I times minus I, which is minus 1, and we have d over d of z times d over d of x, here psi. Here also here for this term we have also minus h bar square d of over d of x d of psi over d of z. And when we take this minus and multiply with this minus, we get plus. Okay, then we have here minus h bar square d over d of z time, we can put this as this one, okay, d over d of c over d of x minus plus h bar square d over d of x times d of c over d of z. But we know that the derivative are, if we take, for example, if we have a function psi which is equal to psi of x and y, then the second derivative of psi here I must write the second derivative of psi in function of x and y, it's equal to the second derivative of psi with relation of y and here z and x, where the order that we take the derivative doesn't matter. This means that this derivative also is equal to this one, so that we have this term has equal to 0, and this is equal to 0. Again, from here, this means that the z component of the linear moment commutates with the p component of the linear momentum. Okay, we go on again. Here we have the same situation where this is equal to 0, here this is equal to 0. Okay, now we go we must analyze this term, which is y p x. Okay, we are acting this commutator on this psi function, and we have y px minus px y acting on psi, and this is equal to y p psi minus px y psi. And from here we have y p x psi minus y p x psi and plus and minus psi p of x y. Okay, this actually equal to 0. This is actually equal to 0, and here we know that this is equal to minus I h bar d of y over d of x, which means that we get here 0 because the derivative of y in function of x is equal to 0, where y here is a variable, not a function. Okay, then we have this term also equal to 0. Again, we can take here we can also take we can analyze this term, and here we have z, and here we have p of x, and we can see that is the same situation as there, and we have 0. Here something's wrong. Okay, here we must have, I think, can I see? Yeah, it's p of z. Okay. Okay, here we have also 0, as here we have 0, 0, 0, then we have that the commutators of x component of angular momentum with the x component of the linear momentum is equal to 0, as we have shown previously with this procedure, because here in this term we have 0, in this term we have also 0, or using the same thing here, we have also 0, we have 0 here, we have 0 there, and we get 0 as the last result. Okay, again, this means that we can experimentally observe in a quantum system at the same time the eigenvalues of angular momentum in a component x, and the linear momentum in a component x of the same system. Okay, we go on solving the last exercise, which is the commutator between for the last exercise, we have now the commutator between x component of angular momentum with the y component of the angular momentum. By definition, we have Lx equal to y p z minus z py, and Ly is equal to z px minus x pz. Then here we will substitute the respective expressions. Minus z py and z px minus x pz, and we have here y pz or z px minus x pz minus z py z px minus x pz, and this is equal to, for the first term, this one we have y pz z px minus y pz x pz. Here we have minus for the second term. We have minus z py z z px plus, because we are conjugating this minus b with this minus, and we have plus z py and x p z. Okay, for now here we have, for this term we have y pz z px plus y z px pz minus, here we have y pz x pz minus y x pz times pz minus, now for this term we have z py z px minus z px py plus, now for this term we have z py x px plus z x px okay py. Okay. Okay, can we compare terms here? I think that no. Then okay, then we go on. Now for this term I have I have y z pz px plus y pz z px plus, for this term I have z y px pz plus y z okay px pz. Now for this term we have minus y x pz pz minus y pz x pz. Now for this term I have minus x y pz pz minus y x pz px. Okay, now for this term I have minus z square py px minus z py z px. For this term I have minus, okay, z px minus z px py plus, for this term I have z x py here, okay, pz plus z py x pz. And for this term I have plus x z pz pz py, sorry, here it's only py plus, now I have z x pz and py. Okay. As we have shown in the previous steps, where here different component of the linear moment commutating between them, and these commutate different component of linear moment commutating with another positions, with other position different of their different from their component. Then, and we have also showed in the previous videos that the commutator between a component, the position with the position with the corresponding linear or component of linear momentum are equal to I time h bar. Then here we have that this is 0. Here we have minus I h bar. Here we have 0. Here is 0 because we have a product of positions that commute between them. That means y times z is equal to z times y. Then we have it equal, this has equal to 0. Here we have that the component of linear moment will every time commute between them, because here is the same operator. Pz times pz is equal to pz times pz. Then we have there 0. Here we have 0. Here also we have 0. Here we have 0. Here we have 0. Here we have also 0. Here we have also 0. Here we have 0. Here we have 0. 0. Here we have ai time h bar, and again here we have also 0. So that we have that the result here is minus I h bar time p z plus sorry, I time h bar p y here. Okay, and sorry, I must verify something here. I have also y here, and I have here y, and in this term I have z x here, then here I have x. So that this equal to minus h bar minus I h bar time oh sorry, what's happened here? Okay, here it's I h bar time x p y minus y time something's wrong here. Oh sorry, this is x, no, not z. Here x, then y px. This is actually, as we can see from here, this is actually the z component of the angular momentum. And then we have here I h bar L z. This means that the commutator of the x component of angular momentum with the y angular component of angular momentum, it's equal to h I time h bar L z. And we can also verify that we using the same procedure that these commutators is equal to h bar L x here, and also we can verify that here we can verify that z x is equal to h y. Okay, it's okay. Thank you very much for watching this video, and again, put like in this, share with your friends, and see you on the next video. Bye.